Hey, what's going on, folks? It's Mike here, and welcome to the C in a Day series. We are already at our 10th day in the C programming language, and hopefully you've been enjoying the series and learning a lot. In this lesson, I'm going to be talking about some of the lower level bit manipulation things that you can do in the C programming language. And this is something that's cool that's available to us in the language, and again, allows us to really think like a systems programmer or even begin to optimize our code. So this is probably something, if you're just starting out programming, that you don't have to worry about too much, but it is useful to know that you can do these things in C, so I do want to show you those things. So with that said, let's go ahead and dive into the code and look at some examples. So the first thing that I'm going to show you is this idea of bit shifting. And if you haven't studied this in a discrete math course or seen this in articles or anything, the basic idea is that we represent numbers in binary. So you might have a set of bits that look something like this. And often we'll group them into fours because it's a little bit easier to read. But let's just say I have something like the following. And this is representing the number 2 here. Okay. So if we count in binary, this is 2, and the rest of the things are 0. Now, what I can do is use these shifting operations to shift my bits to the left here, and essentially move everything one position forward. Okay, so if you haven't practiced your binary counting in a while, essentially if I shift the bits forward here, this will make this, well, let's go ahead and shift this forward by one position here. And we could even assign this a variable if we want, say X, for example. And I'll shift to the left, or sort of rolling in this direction, again, if that's useful. And then we'll get something like this, where, well, 0's in the same position here. And we essentially just move in a new 0 here. 0, our 1 is now here, 0, and then 0, 0, 0, 0, and so on. All of these zeros just moved a position over, and our last 0 is just dropped. Okay, so effectively what we've done here is, well, x equals, and I'll give you a moment to think about this. Well, x equals 4, but x has essentially been doubled, so it's twice as big. So this idea of shifting bits is a quick way to do multiplication. So let's go ahead and dive in and see a code example for how to do this. So what I'm going to go ahead and do is go ahead and just create x, and let's give it a value, say 1 to start here. And we'll just print off what x is and use the format specifier %d and the current value. And then what we'll do is practice shifting those bits here. So x, I'm going to shift over 1 bit. Or each of the positions, I should say, over by 1. And I do need to assign x to this new value here. And then we will just repeat here our print. So let's go ahead and do this a few times, each time shifting over the bits in x by 1 here, and let's see what our result is. So I'll compile, I'll run, and before I run, again, take a chance to pause the video and see if you can guess what the output is going to be for x each of the times. So of course it's going to start off by 1 here, but if we follow this example that we learned about on the right on our introduction to bit shifting, well, let's see what we get. Okay, in 3, 2, 1, well, again, we get the powers of 2. We're essentially multiplying by 2 each time, doubling our size. So that's a pretty neat trick that we can use with bit shifting. And just to summarize, what we've got here is we can multiply or double quickly. Okay, but what about if we shift in the other direction? So if I do x and then go 1 bit in the other way, well, that would be effectively taking all of these values and shifting them over by 1 position. And then this last value just kind of falls off here and no longer exists. So let's go ahead and try it and see what happens. Now this time I'm going to create a bigger number here, something like 64. So this will make a little bit more sense here. And let's just go ahead and do a quick substitute so that we are shifting our bits in the other position, or other direction rather. And I'll compile, I'll run, and you can see the opposite effect. Again, this time we are dividing by 2. So that's the essential idea. Now, in the C programming language, I've sort of illustrated my bits and the sort of least significant bit here and the most significant bit on this side. This is just my representation and sort of an aside. You don't have to worry about the endianness as much, at least at this point in your programming career, but it is something that the compiler will take care of. And if you have to support or switch the endiannesses, there's other tricks to do there. Okay, so just a little aside on that. Now, you might say, well, Mike, this is cool. Why are we learning this? Well, again, we can multiply or double quickly and divide quickly as well. And this turns out to be a very efficient operation for us to perform on our machine by just being able to shift bits. It's much cheaper, for example, than actually going through and doing a multiplication or divide to just in the hardware do this division here. And oftentimes we do end up working with powers of 2. So again, there's value there. Now, another use case that might be a little bit more interesting, but is perhaps more domain specific, is if you're working with some sort of data. So for a moment here, allow me to explain if you have some image with some figure here. These images are made up of pixels. So if you haven't heard the term here, so here's a pixel here, and there would be another pixel, another pixel, another pixel. Again, that's how we represent or talk about images. Now, each of these pixels are generally made up of a red, green, and a blue, and sometimes an alpha component here. And those values typically range between 0 and 255 for each of these. So this is sort of a pixel format here for your image. So again, why am I talking to you about this? Well, there's actually a nice trick that we can use with bit shifting to compactly represent pixels in just a single integer. So allow me to illustrate this with an example. So I'm going to go ahead and get rid of our example here so we can clear things up here. And again, what I want to do here is just create some pixel value here. And I'm just going to make something up here. Now, what I'm going to change in this example, something that we haven't seen, is represent this in hexadecimal. So I'm just going to provide some numbers here, CC11, so something like that, something reasonable. Now, again, this is the hex number representation. I could have easily done this in decimal, but you'll see why in a moment when I actually do the bit shifts, why this makes sense. And let me quiz you for a moment to ask. If I needed some number of bytes to store information, that is the value 0 to 255, how many bytes would you need? And the answer to that is, well, you'd need 1 byte. And we've seen that before with an unsigned char or a char type here. Okay, so the idea is going to be that I can store my red, green, and blue. So red here, I'm going to represent with FF, green with AA, blue with BB, or excuse me, CC, and the alpha component, which is how opaque a pixel would be, with the numbers 1, 1, which in hex, 1, 1 equals 17. So you might want to brush up a little bit on your hex. This is 16 times 1, and this was to the power of 1, and then this would be just plus 1 here, okay? And let me actually do 16 to the 0 times 1 here, okay? So how do I extract out those pixel values from this single integer? And again, the point of doing this is for perhaps simplicity. I can just represent each of these pixel values with a single integer rather than having to create a red, green, blue, and the alpha or opacity values here. Okay, so if I'm sending data across a network, for instance, it might be a little bit more of a compact representation. Okay, so let's go ahead and extract those values using the bit shifting technique, because eventually we do want to, or may want to, figure out the red value and the green value and so on. So I'll give you a moment to think about this, but if I have my pixel here, which direction do I want to shift it to such that I can get, well, the component here for red, okay? And this might take a little bit of moments to think about here, so let me try to, again, give you a hint here. So recall that each of these represents a value from 0 to 255, so we can think of this in terms of bytes, but it's probably a little bit easier if we think of things in terms of bits. So 1 byte would be 8 bits. So let me go ahead and give you some clues here. 1 byte, again, equals 8 bits. An integer itself equals 4 bytes on my architecture. So if I only really want, and then I can think of this as 32 bits. So I really only want 8 bits from somewhere. So how many of these things do I have to delete here? And I've highlighted some for you. All right, if you've had a moment to think about it or have paused, I'm going to reveal that we want to roll our bits or shift things to the right 24 bits here. So effectively what I'm doing here, and I'll just use my example here with red, green, blue, is to take the red value and just shift it over all the way to this last position here. And an unsigned char itself can only hold the 8 bits or 1 byte inside of it. So this effectively becomes the red value here. Okay, and then all of these values here just go away. They're essentially gone. Okay, so let's go ahead and see this in action here. And let's just go ahead and do a printf here and say r is, and let's see, we have a unsigned char value, so I'll represent that with C. And I'll just go ahead and put r here. Okay, so let me go ahead and rerun this. And oops, we don't see anything here because I actually want to print out the number here. So %d here. It is a char value, but there was likely no meaningful value that would print anything out. So let's interpret this value in r as a number here. So r is 255 here. Okay, so that's what we have here. And we can see that that is ff, which again, you can go ahead and do some of your math here. So let me go ahead and help you out. Again, this isn't a lesson in hex, but it's useful, again, just to confirm that ff, if I'm doing this, I would do 16 to the first power times what is f in hex, 15, plus, well, this next value here, 16 to the 0, which will just effectively give me 1, times 15. This value here is 240. I have verified on a calculator. I don't memorize these things. And then this is just 15, which gives me 255 here. Okay, so let's go ahead and finish this off for the rest of our pixels, and I can show you how to extract all the values here for red, green, and blue. But I am going to pause here for a moment to give you a chance to do this exercise yourself. All right, so if you have paused, I'll go ahead and show you what the shifts are. And for green, well, that would be the next component here. And again, we can label here. This would be red, green, blue, and alpha. And for those of you who go on to work in graphics, you'll find that there are many ways and many orders to put these things, but I'm just giving you R, G, B, and A. That's a common one. So I would need to shift over 8 bits for the A, 8 bits for the blue, which gives me a total of 16 here. Okay. And you might be wondering, well, Mike, what about these bits at the end here? Well, since I'm interpreting this as a unsigned char, we effectively only are taking in or able to store 8 bits. So those are essentially truncated or lost. Okay, so with that in mind, if I'm looking at blue, that means it's just 8. We just need to shift over and get rid of these 8 bits for the alpha. And if we're at the alpha, well, let's just shift over nothing or 0. Okay, we don't need to do any work. Okay, all those other bits will get truncated off. Red, green, blue, alpha. Red, green, blue, and alpha here. Okay, so let's go ahead and recompile this, rerun it, and you can see the associated values. And if you'd like, and if you're just getting started, I would recommend just verifying that AA is in fact 170. So 16 times A is 10, 160 plus another A, which is 10, is 170, and so on. So you can get a little bit of practice with hex and thinking about some of these different number systems as well. Okay, so that's the first thing that I really want to show you, this idea of bit shifting, how you can multiply things quickly, divide, but also use this as a tool to compactly represent things within an integer. Now, let me go ahead and shift gears a little bit here and talk about something else related to this concept. And this is also going to be related to thinking about things in terms of bits in the C programming language. So let me go ahead and get rid of my code here. I'm going to clear my canvas so you can just see how we worked from backwards, again, talking about RGB, compact representations, and then learning about bit shifting. And this time I want to talk about something related, so I'm going to leave the word bit here, but we're going to talk about bit fields. Now, in today's lesson, things have been a little bit different because previously we've always talked about things in terms of bytes when we've used things like size of, for instance. And I think that is something that's distinguishing this lesson from perhaps the other ones. But again, something that's really cool and exciting about C, that we can think about things with bit level precision. Okay, so let me go ahead and set this up with another example. If you've ever played any games, say Mario, Pac-Man, or just any sort of computer game, oftentimes you might want to play through that game, and there might be different stages or different levels of that game. So you might have some sort of structure, for instance, that's called games, or maybe stages completed. And the goal of this structure is to hold information about what has been completed in the game. Maybe level 1, level 2, level 3, and so on. And you might use some sort of value to represent this stage here, int, and just be able to store either a 1 for completed or 0 for this particular level to indicate that, yes, this stage has been completed, so move on the next time the player starts the game to level 2, or next time you start the game, move on to level 3. And this was a reasonable representation of a data structure for this type of problem, but it is slightly wasteful. So let's go ahead and observe by creating this structure here, stages completed, and then see if we can more efficiently represent it using some of the things that we're learning about, that is thinking about bits in this lesson. So what I'm going to go ahead and do here is go ahead and create that structure, and I'll use a type def here so we can make it a little bit easier. And I'm just going to call it stages completed. Okay, and then maybe we have something stages completed T for the type. And let's give ourselves a reasonable amount of levels here to be completed. Level 1, state maybe, or level 1 completed, and just a 1 or a 0 value here. And let's just create a few of these here. I'm going to create a specific number here. Let's go ahead and try maybe, let's do, oh, I don't know, 5, 6, 7. How about 8? 8's a good round number, and that seems reasonable here. Now, what I want you to do before I proceed is tell me or think about how many bytes this data structure takes here. Okay, and as I'm typing out our tool here to printf, so number, or rather, let me make this even easier, size of stages completed equals, and %ld, because we have a unsized, or excuse me, a unsigned number, and then we'll put the size of. And I'll go ahead and put this on a different line just to make it a little bit neater here. Stages completed. Okay, so go ahead and hold or lock in your final answer, so to speak, here of how many bytes this actually takes for a structure. And in 3, 2, 1, I'm going to reveal. I'll hit enter, and 32 bytes of information. Why 32 bytes? So let me illustrate this through level 8 here. Well, 8 integers times the size of an int on my architecture, which is 4, equals 32 bytes of information. Okay? And you might say, well, Mike, we were only storing a value of 0 or 1 in our specification. Was it complete or not complete? So how could we make this more efficient? And go ahead and take a moment to think about that. And if you've taken a moment to think about it, you might have said, Mike, well, this was really silly that you even used an integer. We have a smaller data type, a unsigned char. Let's go ahead and use that. Or we can even just use a char, because maybe we want, it's just a little bit easier to type here. So let me go ahead and speed this up here. So change our ints to chars. And now let's do the same experiment here, knowing what we know about the size of our data type, and go ahead and make your prediction what the size of is going to be. And if you've gone ahead and made your prediction, let me go ahead and just make sure I've saved. I'll recompile and I'll rerun. And this time we're down to 8 bytes of information. And again, that makes sense. If each of these are 1 byte, then we should have a smaller data structure here. So here's where bit fields actually come into play here. The topic that we are discussing that's new for you is that we can actually specify using the C language how many bits we actually want this information to take up here. So let me show you how to do this, and it's actually relatively simple. After each of the data types, I just put a colon and then how many bits here. And because I'm only representing a 1 or a 0, I only need 1 bit on or off here for this example here. So let me go ahead and just put in the 1s here. And then I'll go ahead and recompile. And again, if these are only allegedly taking 1 bit, then go ahead and make your predictions as to how much data will be required here. And I'll go ahead and run it here. And you're going to see now we only have 1 byte of information here, which is exactly as much as we actually need. So this is pretty cool that this actually works here. And we can see how much information that we were actually able to save, or how much memory that is. Remember that we started off with 32 bytes, and then we picked a better data type, and then we were down to 8 bytes. And then ultimately we were able to decrease this down to 1 byte using this idea of a bit field. Now, how do you think that C is actually representing this particular structure, or able to get away with these manipulations? Well, effectively, when we're just using 1 bit here, there's probably some bit shifting mechanism going on saying, hey, when we access this field or this field, offset or shift by 1 bit to get to the next field here. Instead of moving down 1 full byte, or if we have an integer, 4 bytes to access the next field here. So we have to think a little bit low level if you'd like to think a little bit more about the actual mechanism for implementing that. But for now, we can just think about this as, hey, if we only need 1 bit here, then just use 1 bit. And you might say, well, Mike, what about if we wanted some intermediate stage here? So where we could have a 0, 1, or maybe a 2 means something, or a 3, and so on. Well, again, we could increase our size here. So let's go ahead and just do that experiment. Let's make these all 2s, because maybe there's some completed, not completed, or in progress state here. And again, you can see that we're still only using 2 bytes of information. Okay. Now, it may also be interesting for you to see is, let's say we don't have a perfectly nice number like 8, which 8 bits makes 1 byte exactly. And let's say I'm only using, or trying to use, 3 bits here. Now, when I try to run this program here and compile, well, the C compiler is still going to pad this data structure with 5 bits. I can't have a just 3-bit structure. 1 byte is the minimum amount of information that I can address in the C programming language. And in fact, I don't know many other languages where you can, at least on a normal desktop computer, address anything in a more finite granularity. This is just how the hardware works. All right. So folks, I hope you found that lesson interesting. I think this is a really powerful technique, and for folks who really like to think about what's going on in the machine, or perhaps have an interest in optimization, these are fun topics to know about, in my opinion. This idea of how we can most compactly represent information. In a way, it's sort of like a puzzle, which can be very exciting for folks to figure out how to compactly represent some piece of information and improve the overall performance of a program. So if you've enjoyed this lesson, if you've been enjoying these series here in the C in the Day series, please go ahead and give it a like, give it a subscribe if you're not already subscribed, and be sure to comment below if you know some other cool bit hacks. There's tons and tons of them that can be done that we haven't even explored, but I think they're very fun, and maybe you can share some that you discover with some other folks in the comment sections. So we'll see you next time, folks. Thanks for your time and attention.